And welcome to day 1 of Unit 3. We're going to finally get into some calculus with the start of derivatives. Today we're going to look at the idea of instantaneous rate of change. So let's look at what just rate of change means in the first place. You're taking a car trip with your family and your phone died, so you're bored. So you start keeping track of how far you travel every few minutes. The distance traveled is s. It's a function of time t. So when we look at this, it says find the average speed between 1 p.m. and 4 p.m. So we've got 1 p.m. We don't want to write, of course. 1 p.m. and 4 p.m. When we're trying to find average, we're going to take the two of them, 2 points, so 1 comma 50 and 4 comma 200. And what are we going to do with that? Well, we're going to figure out how far we traveled, 200 minus 50, and divide it by the hours that we traveled, 4 minus 1. We get 150 miles over 3 hours, and we know that that's also equal to 50 miles per 1 hour. So that's the average speed that we traveled from 1 to 4. If we look from between 3 to 4, I think you're going to realize that we're going to go a little bit faster just between 3 and 4. So we're going to get 3 comma 125 and 4 comma 200. With that, I'm not going to show the math. 200 minus 125, 75 miles per 1 hour. So we're on the throughway there. Maybe here we're on some back roads, or over the entire time we're on some back roads. Well, what this is showing you is that, of course, average speed can change based on the interval that we look at. So probably on the expressway here, probably overall, maybe some expressway, but some back roads too. So when we look at this, what did we just do here? Well, we just found the slope. We found the slope. Slope is another word for average rate of change. And so another example of this would be, this is exactly an AP question. This is a AP question that I took off of the previous exam. A pot of tea cools, and it's given that this is some of the data values that were collected. So it says approximate. As soon as you see the word approximate, we know we're going to find the slope. The rate of change at which the t is changing at 3.5. Where you look and go, well, there's not 3.5, but no, but what is in between 2 and 5? But 3.5. And so the idea here that we're going to do is we're going to take the average between the 2 and the 5. So we're going to go 2 comma 60 and 5 comma 52 and find the slope. So 52 minus 60 divided by 5 minus 2. We're going to get negative 8 degrees Celsius per 3 minutes. That's the average rate at which it's changing right around 3.5 minutes. Again, I understand that it can change. We're looking at just 3.5, so that's why we did between 2 and 5. If I had asked for 7, we would have gone between here. If I had asked for 6, probably would have gone between 2 and 10. It's just what the question asks. When we look at average rate of change, we already stated that the average rate of change is just the time between 1 point and 2 points. It's a straight line. It's a slope, it's a secant line, it's the slope of the secant line between those 2 points. And it's just finding the average of change. We understand that it can change. Instantaneous rate of change is when you look at the limit. And I'm going to show you here. If you look at this, the instantaneous rate of change is based on the exact moment that it is changing at that value. Notice that this red line right here, this red line right there, is the secant line. Notice what happens as this point, the far right point, gets closer and closer to the fixed point at 2. As it goes so close to it, right there, that's the instantaneous rate of change. But notice that if I go right on top of it, that line goes away. So the idea that that's the instantaneous rate of change, right there, okay, right as we approach it, the only way we can get that is to find the limit as the one point connects to another point. Okay, and it gets really close to it. So the key is that if I was given that function there, and I'm looking at that point this point has to get so close to that point that it's got to approach it, but never actually be on it, or as you saw before, it actually goes away. And so that's the instantaneous rate of change. It's found by taking the slope, the limit of the slope of the secant line. So, if y equals f of x, then the average rate of change with respect to x over that interval is f of x1 minus f of x sub 0 all over x1 minus x0. That's all it's saying is the change in y over change in x. This is the slope. Okay? That's the average rate of change. The instantaneous rate of change is found by doing the same thing. But you're finding the limit as x1 approaches x sub 0. That idea that if that's x sub 0, that the point on that line gets so close to it, and it's basically approaching x sub 0, but we know the limit is not actually what it's on, it's as it approaches it. So that's the instantaneous rate of change, the limit of that. So that's what instantaneous rate of change equals. This right here. That's the key for today. If we look at this first example here, average rate of change, again, that's slope. Okay, we don't want to write slope. So I found the 2 points, and I found the slope. Hopefully that makes sense to you. What I want to look at is the instantaneous rate of change when we go to -4. So I wrote down the definition again. The limit is x1 approaches x sub 0. We got to figure out what our x sub 0 is. That's what we're approaching. Well, that's what we want to find right here. So we want to approach -4. Excuse me. So what we're going to do here is x1 approaches 4. We are not going to substitute in for x1. So we got f of x1 minus f of -4. That's a 4. Over x1 minus -4. And the idea here will be, well, what is x1? F of x1. Well, we got to go back up here and say, if I plug in x1 into that, I'm going to get x1 squared plus 1 minus 17. That's what f of -4 is, in case you want to know that. Okay, all divided by x1 plus 4. Well, why is that nice? You get x1 squared minus 16 all divided by x1 plus 4. We know that that can factor those cancel, and you're left with -4 minus 4, which equals -8. And so that right there, I want to see it better, is our instantaneous rate of change at that exact moment for the function x squared plus 1. So again, just to recap, use the definition as instantaneous rate of change. Found what f of x1 was. How did I do that? I plugged it back into the original function x1, so x1 squared plus 1. Found what f of -4 was, got 17, divided by the two x values subtracted from each other. Found out that I can factor that, and find the limit by factoring and canceling in this case. So I canceled the two common factors, plugged in -4. -4 minus 4 equals -8. So now it says find it at any general point. Well, what do I mean by general point? Well, limit as x1 approaches x sub 0 of f of x1 minus f of x0 all over x1 minus x sub 0. Well, what am I going to do there? Well, f of x1 we already know is x1 squared plus 1 minus parentheses x sub 0 squared plus 1 all over x1 minus x sub 0. Oh, oops, bad notation on my end, my apologies. Well, what do I get here? Well, these ones, because I got to distribute at negative sign, will cancel. So I'm going to get x1 squared minus x sub 0 squared over x1 minus x sub 0. Well, I again look, nothing quickly cancels here, but I notice that I have a difference of two perfect squares. x1 plus x sub 0, x1 minus x sub 0 over x1 minus x sub 0. Those cancel. I'm going to plug in for what I know. I notice that x1, that x sub 0 is going to replace x1, so I'm going to get x sub 0 plus x sub 0, which equals 2x sub 0. That's now my generic instantaneous rate of change, meaning that at any x value I can plug in x sub 0 to times multiply by 2 to get the answer. Notice that if I go back up here, I had negative 4. Well, what's 2 times negative 4? Negative 8. And so this was a specific, at a specific point. This here is at a general point, x sub 0. You can look and figure out from the previous one that x sub 0 was negative 4 from the previous example, and we get the same answer. So this is our instantaneous rate of change. One more example here. The last example here deals with a particle moving on a line away from its initial position. After t hours, it is s equals 3t squared plus t from initial position. Find the average velocity between 1 and 3. I did that work for you. We don't know the actual units, whether it's centimeters, meters, whatnot, so just units per hour. Find the instantaneous velocity at t equals 1. So instantaneous, again, we're going to look at the limit as t1 approaches t0. Well, what is the actual point that we're looking at? We're looking at 1. So we've got to approach 1. We're going to get s of t1 minus s of 1 all over t1 minus 1. Now, the key here is that this is our function right there. And so we need to plug that in. What I want you to do right now is pause it, see if you can do this from using the previous example, and when you're done with that, unpause it, and I'll have the answer here for you. And so hopefully you got the answer to be 7. I have all the work here. This is how I factored 3t1 squared plus t1 minus 4, and you can pause that and look at it. We're going to go on to letter C. And so what I would like you to do for C is just remember the fact that we're looking at the generic value of t sub 0, so we're going to be able to find out what the instantaneous rate of change is at any t value, but we're going to use 3t squared plus t, and hopefully you can plug in and find out the answer to this. Pause it, and I'll have the answer when you come back. So probably most of you are trying to say, well, how the heck do I answer this with it looking so crazy? Well, the reality is right here, you need to learn how to rearrange it. And it's not an easy thing. Don't think that I was sitting there going, I expect you to know this. But before this time ends up, so hopefully we got to that point. What I can do is rearrange it so that the t squareds are together. And if I factor out a 3, I'm left with 3t1 squared minus t sub 0 squared plus that. Well, I notice that this is a difference of two perfect squares, and so I can factor that out. Now notice that I have all of this. This is one big term multiplied together, plus this. If you want to call it a term, it's not really, but plus this part. Notice that since this is all multiplied together, I can take out a t1 minus t sub 0. If I can factor that out, I can have t1 minus t sub 0 be a factor and cancel with the denominator here. So what I did is I factored it out, and I'm left with this multiplied by that. Okay, so I can cancel those two terms. Since I'm looking for t1 approaching t sub 0, I can plug in t sub 0 wherever I see t1. That does not look like a 0 there, but that was meant to be a 0. So t sub 0 plus t sub 0 is 2t sub 0 multiplied by 3. You get 6t sub 0, and add it to 1, and then that is our final answer. That is the generic value. So hopefully that makes some sense to you guys. You can ask me questions in class tomorrow, and I'll see you guys. Enjoy your night, day, whenever you're watching this.